Okay, so I feel like we talked about this already. Stable isotopes exist for 1 to 83. Low mass numbers, less than 40, you have usually a balance of protons and neutrons. That's because the strong force is enough to overcome the electrorepulsive force. But once you get mass numbers greater than 40, then you need to start adding neutrons in order to hold the thing together, because electrostatic repulsion gets so strong. It starts to dominate. So you need to add more neutrons to add more strong force in order to hold them together. This is just kind of interesting. If you're looking at the stable isotopes, okay? Stable isotopes. Here's a list of stable isotopes, and here's a bunch of stable isotopes. What you find out is that if you have an even number for your mass number, in other words, even numbers of protons and neutrons, you get many more stable isotopes. And it's not clear exactly why that's happening. It has to do, they tend to like to pair off. And if they do pair off, then they tend to be more stable. So we think that has to do maybe with some of the atomic, or the nuclear shells. So you have more stable isotopes. More stable nuclei have even pairs of protons and neutrons. They like to be in pairs. There are magic numbers, unusually high number of stable isotopes at given mass numbers. So these are kind of your magic numbers. You get lots of isotopes that have a mass number of 50, like proton-neutron combinations. And you have several more that have 82. There just seem to be a preference to be at those particular mass numbers, which seems to have something to do with the sort of shell nature of these isotopes. Okay, binding energy. You've now seen this curve a couple of different times. Iron is what we consider the most stable. These are stable also. Okay, the really small ones are stable because there's just a couple of the protons and neutrons. But once you start getting more and more neutrons and protons, the maximum stability is going to be right at iron. Okay, so I think this is a little bit confusing, but the idea is you're going to need, if you have an iron atom, you're going to need the most energy to break it apart per nucleon. It just loves being together. So it's like it almost has the lowest amount of potential energy. So you talk about different sort of energy levels. Iron would be down here, and then hydrogen and helium up here, and helium up here, and then uranium. So the idea is like this is the happiest one. It's totally bind. They're a really close family. You want to break them apart. It's going to take a lot of energy. So like everybody wants to be like that family, right? They want to have that close-knit sort of feeling, and so they're going to try to get there. And that's what's going to drive sort of the fission and fusion that you guys are going to be reading about and doing your little exercise here in a little bit. It is interesting that helium is like a little aberration. It's like a perfect geometry of protons and neutrons, and the way they fit together, it's very, very stable. And that's one of the reasons that we see alpha particles. Very stable little chunks of protons and neutrons that get kicked out in when we see radioactive decay at the higher level mass numbers. Why not all neutrons? Yeah, so here's a question. Why, if neutrons, if we have this strong force, why don't we just have neutrons? Why do we even have to have protons? Because the protons repel each other. You know, it seems like, why would you want to have them in your family if they're always fighting, right? Well, it turns out that from a quantum mechanical standpoint, they have energy levels that, with sort of shells, and those shells have to be filled in order of energy level, and they have to have protons and neutrons. So you can't have a family without having the protons. So you can't have a neutron-only family. So you won't have 8 neutrons and 2 protons. You're going to have like 1 proton and then another neutron and then another proton and then another neutron. So they're going to kind of balance out to fill up those shells. So that sort of complexity that you've seen with the atom and electron shells. Remember the SPDF and all of those kinds of things? Very similar type of idea, except more complicated when you're talking about the nuclear energy levels. Just the decay series or chain, you kind of worked this when you did your homework problem. You know, where you have one atom and it goes through an alpha decay and then a beta minus and then a beta minus and then alpha and then alpha and then alpha and then alpha. And so they can trace and see, if you start with something like how does it decay? In what way does it get from here? Eventually it wants to get to something that's stable. And so this is where it ends up, lead. Okay, lead is considered stable. So it's going to keep decaying. Some of these decays are really quickly. So this is 1.4 times 10 to the 10th years. That takes a long time for it to decay. This is 5.7 years, 6.1 minutes, 1.9 years. So the decay happens at different rates, but eventually it's going to get from unstable to stable through a very long series of decays. Decay rates and activity. This is where we're going to get into kind of math. You have several problems tonight on decay rates, and I think they're kind of fun. And we've set them up mathematically to be mathematically easy for you. So let's take a look at the ideas here. First of all, when we're talking about decay, the number of decays per second is the SI unit. Okay, how many decays in a second? It's called the becquerel. The first unit that they used to describe decay was a Curie, because the Curies were the ones who were studying radioactivity. So this is what they came up. Well, they defined the Curie, and then the becquerel became the SI unit, and so here's the conversion. We'll typically work in becquerel. Okay, so we're going to have a new constant, decay constant. And Eric talked about when you have carbon-14, it decays at a very constant rate. So you need to have a constant that shows that decay rate. And so we have lambda, not to be confused with many other lambdas that we've seen throughout the year. So the lambda represents the constant for the decay. So you have delta n equals minus lambda. The minus means you're losing whatever kind of material you started with, minus lambda times n delta t. So this is considered the activity equation, okay? Lambda n equals minus delta n over delta t. And you see delta n's and delta t's, and if you're a calculus person, you might think about how that looks like a little bit of a partial differential. And then you could take this, and you could integrate it, and you could get this, okay? So this is the governing equation that describes what happens in radioactive decay type of behavior. So it's going to create, it's an exponential, which means it's going to create a little graph that's going to look like this, okay? It's an exponential, actually that's not very good. It's going to go more like that, okay? So it's going to drop off quickly. And I have a good graph, and I'll show it to you here in just a second. So this is the equation that is going to govern radioactivity. Now, we can come up with a couple of simple equations that help us to solve problems. One question they often ask is, given this activity constant, then what is the half-life for the material? What is a half-life? That means, like, if you start with 1 kilogram of material, how much time does it take before you only have a half a kilogram left? What is that time period? Because that time period will be constant, given that your lambda is a constant. And so in order to find that, we can just solve this little equation for that time. And so it's going kind of fast here, so let me take you through it. If you rewrite this as n over n sub 0 equals e to the minus lambda t, okay? And then when you want to solve an exponential, when you have a variable, remember you take the natural log of both sides, you get the natural log of n over n. I'm not going to make you do this. I'm just showing you where this equations come from that you're going to use, okay? Take the natural log of both sides. If we want to know what the half-life is, in other words, what is the time that half the material is gone, then I'm going to have a half of the material left, so I take the natural log of 1/2, which gives me 0.693. And that's going to equal that decay constant times that half-life time period. And so that gives me an equation that looks like this. The half-life, meaning the time it takes for half the material to be gone, is equal to 0.693 divided by lambda, that decay constant. Again, that comes from just solving this equation by solving it for t, the half time. So that's an equation you can use. Another way you can write it, it's kind of hard to see because of the funny little logo there, so I'll rewrite it over here. Another way to think about it is like this. N equals n sub 0 times 1/2 raised to the t over the t to the half time, okay? And that's an equation that you're going to be using. That's the one you're going to use, sort of. Like, I'm not going to have you solve it by taking the logs of both sides, but you're going to kind of use it to sort of eyeball how to solve one of these problems. So you might rewrite it as something like this. Like, let's say I gave you, this is the original amount of material you started with, and this is after a period of time. So if you rewrite it, you're going to get n over n sub 0. And what I'm usually going to do is I'm going to kind of give you some combinations of material. So, and it's going to work out so that, let's say I have a 1/32 of the amount of material. Like, I'll give you numbers that turn into a fraction that's 1/32. Does that make sense? So, so that's going to be 1/2 to the t over that half-life period. And the question might be, and I tell you how long it takes. Let's say it takes 1,000 seconds. I say in 1,000 seconds, you could basically have 1/32 of the material that you started with. Okay, does that make sense? Yeah. Okay, so then you have this, and you say, well, what's the half-life? Okay, well, think about this. This is 1/2 to some power, right? 1/32 is 1/2 to some power. What power is it? Yeah. It's to the 5th power, right? So this is 1/2 to the 5th power. So then you just say this is equal to 5. That's what I mean by kind of eyeballing it. Like, you don't have to, normally if you were solving something like this, you'd take the log of both sides, and it's a pain. You don't need to, though, because we're keeping it simple for you. So you'd say 1,000 seconds over the half-life is equal to 5, and then you solve for the half-life, and you get, it's like 200 seconds. Does that make sense? There's another way to do it, too, and I'll show you an example here in just a second. Another sort of eyeballing technique. So first of all, think about this. When you have radioactive decay, it's like an hourglass. So you start with all of your material, and then after one period of time, okay, one half-life, you're going to have half of it left. So if you have 100%, then only 50% is going to be left after one time chunk. And so you're going to have a mix of 50% of what you started with and 50% of something else, whatever it's decayed into. Okay? And then you go to another half-life, and you've lost another 50%. So now you go from 50 to 25. And then you go another half-life, now you have like 12.5%. Another half-life is half of that, 6.25%, etc. So every time you go one time increment, you have half left. And that's what your little curve is going to look like. So here's an example. Okay, this is like typical of the type of problem you'll have in your homework tonight. A sample has initially 1 times 10 to the 6 radioactive atoms. After 800 seconds, there are 62,500 of these atoms left. Find the half-life of the atom. Okay? So first of all, you got to identify what are these things that we're being told. What do you think 1 times 10 to the 6 represents? That's the initial, n sub 0. And then the 62,500 represents n. And then what is 800 seconds? That's the t. Good. Okay, so now we set up our equation. N equals n sub 0 times 1/2 to the t over the half-life. And we plug in, we get n over n sub 0, 1/2 to that t over the t half-life. And 1 over n over n sub 0 is 62,000 over 1 times 10 to the 6. What turns out is 1/16. Pause, sorry, going too fast. So back up. It's 2 to the something. So 1 over 16 is equal to 1/2 to the something. Yeah?
So since it's always like halved, does that mean that it'll never reach 0? Or, because like the graph was like kind of like an asymptote.
I'd say mathematically so. It seems that, right? Yeah. But eventually it will. It will completely decay. Okay, so 1/16 is 1/2 to what power? 4th power, right? So now you're going to say, all right, that is equal to 4. They're basically going to take 4 time increments to get down there. And so now you can solve algebraically. We know 800 seconds is the time. I want the half-life, and you solve and get 200 seconds. Okay, so this is the kind of problem you're going to be doing tonight in your homework. Now, if the math doesn't speak to you, try it this way. Okay, make yourself a little graph, and have the graph show how much you have to start. Right? You're going to have 1,000,000 atoms to start. After one half-life, you're going to have 500,000. After another half-life, you're going to have 250,000. and then 125,000, and then 62,500. Aha, I got there. Okay? So this is what I'm saying. Like, if you don't want to do the math and kind of think it through it this way. How many half-life chunks is it going to take to get to 62.5? Well, 1, 2, 3, 4. It took 800 seconds. You have 1, 2, 3, 4. Divide that up into equal chunks, and you're going to get 600, 400, 200. So that the half-life, one half-life period is going to be 200 seconds. So you get the same answer if you do it mathematically or graphically. So the good news is we're going to keep the math simple for you. You're not going to have to solve radioactive equations using that original formula that had n equals n to the e to the minus lambda t, although you totally could, right? In a college level class, you would definitely be expected to do that. All right. So this is getting into what Eric was talking about, which is carbon dating. C14 is created in the upper atmosphere, half-life of 5,700 years. The ratio of C14 to C12 has been roughly constant throughout time in living things. So you create the C14, but then it will decay over time. So when something dies and it begins to decay, the C12 remains. So if you imagine that you have that little curve, you can do a little analysis and say, well, how much C14 is there? And you say, well, it looks like there's about this much. Okay, so you get a little analysis and you look on the curve and there's about this much C14 to C12 relative. And then you can back up and say, all right, well, how many half-lives have happened since then? If the half-life is 5,700 years, how many have happened? Well, 10. Okay, well, then it's 50,000 years old. Carbon dating only works for organic material, things that are living, right? So trees, people, bones, remains, that kind of stuff. You can carbon date those. It doesn't work for living things. Okay, but we can use the same concept to measure the how old the Earth is using geologic dating. Bless you. So we found old rocks and minerals with crystals that have locked in original elements. So they've been a closed system. They weren't allowed to decay. As some elements decay, daughters remain in the proportions of materials with long half-lives. So U-238 has a half-life of 10 to the 9th years. And so they can use the proportion of U-238 and what it has decayed into to see, well, how long has it decayed? And then they can backdate how long has the Earth been here. And that's what they've done. And so they found out that the Earth is about 4 billion years. And they've been able to use that. That's like one way of measuring the age of the Earth. There's other ways too, and they all seem to give us about the same time frame. 4.5 billion years. Okay. Concept question. Here we go. For stable nuclei of large mass number, the number of neutrons is stable nuclei of large mass number. The number of nucleons is, everybody? Larger. You need more neutrons to hold that guy together. Okay. And then the nucleus of a small mass number that has too few neutrons to be on the band of stability. The band of stability is that dark line that shows all the stable isotopes. The nucleus of small mass number has too few neutrons to be on the band of stability will undergo which type of decay? Okay, it has too few neutrons. Alpha? Beta plus? Positron? None of these. But positron is a beta plus. Okay, talk it over. Just make sure that you know that there's multiple ways of saying it. All right, so what do you think, Dana? C? Excellent, that's correct. Yep, so you want to have an extra neutron. You're too few neutrons, so you're going to take a proton, you're going to convert it to a neutron. In order to take a proton and convert it to a neutron, you have to kick off a positive charge, beta plus. You're good to go. Okay, here are some tips. Make a quick note of them because I'm going to move on. Use page 966 to help you on these problems. For problem number 37, wait, that's not right. Those numbers are wrong. No, you already did those. But it's great you have homework help on homework problems you've already done. Yay. Okay. All right, so very briefly, a couple more slides, and then I'm going to send you off on your own to work on a project. Just talking about what we've talked about so far, neutrons, protons, they are competing with electromagnetic repulsion and a strong force, binding energy found by the mass difference between the bound atoms and separate constituents. Radioactivity, many nuclides are unstable. They'll spontaneously, though not maybe frequently, decay by emitting alpha, beta, or gamma radiation. The rate is described by the half-lives. Okay, so that's kind of what we did up till now. Today we're going to talk about nuclear reactions. So just to kind of show the difference, a chemical reaction is where you take, water and it breaks into hydrogen and oxygen. The atomic constituents themselves are unchanged. That's just that they're rearranged. So this is going to get, you're going to get energy. Is going to be the energy that comes into play is dealing with the chemical bonds. Okay, so those were chemical reactions. That's what you did mostly in chemistry. So what we're talking about is nuclear reactions. So you have nitrogen and you add helium and you end up with oxygen and hydrogen. So a very different type of reaction where the atoms themselves are actually changing by having an exchange of protons and neutrons. So the neutrons and protons rearrange to form different atoms. Energy, in this case, is given off if the rest mass of the initial particles is greater than the rest mass of the final particles. Does that make sense? So you're rearranging, you lose a little bit of mass, that represents energy. So you can get energy out of those types of reactions. When you're dealing with nuclear reactions, you have a conservation of mass number. So the total number of protons and neutrons is conserved. Also, conservation of charge, momentum, and energy. Necessarily rest energy because mass is turning into energy. Okay, so I'm going to show you one slide on fission. Fission, when you have heavy unstable atoms, they might break apart, but it might not happen very often. It might help to bombard them with a neutron. So if you take a U-235 and you crash a neutron into it, it will become a U-236 at an excited state. So it's high energy, okay? And once it gets into that U-236 high energy, the half-life for U-236 is very, very small compared to U-235. Well, compared to anything, it's very, very small. And so it will almost spontaneously break into two new atoms, barium and krypton, plus 3 neutrons. Boom. Why do you say boom?
Because that creates a chain reaction that sets everything off.
Because you have 3 neutrons, and each of those neutrons can go find a friend and get them all excited, and then they break into 2. And then they have 3 neutrons that find a friend, and they get all excited, and they break into 2. And it happens really quickly, and every time there's a break, there's energy released. So this is what's happening with fission and chain reactions, okay? So a fission reaction will release about 200 mega electron volts of binding energy. Daughters are higher than their parent. Compare that to about 11 electron volts per atom for a uranium chemical reaction. So you can get enormous amounts of kinetic energy released. Okay? So what you're going to do right now is I have shared online a Google Doc, and I put it in your school loop as an assignment for tonight, so you can find the link there. I'm going to put you in groups of 4, and so you're going to group up, and then you're going to work on answering the questions. What time is it? It's 9:45, and I have until 9:30, right? So let's go a half an hour on these and get as much done as you can. And you can kind of divvy up the questions and work them all, and then kind of try to go over them together, right? Because you're going to use this Google Doc to help you to do the to help you do your homework tonight.